Here are some more examples of drawing rigid body free body diagrams. And so we're going to be analyzing in this first one this beam that's right here. So we will draw something that looks reasonably like that. Doesn't have to be fancy. Could be just a line. We usually try to give it a little bit of depth there. That's kind of ugly, but nonetheless, there is a weight. There's the weight of the beam itself. Sorry about that. There's the weight of the beam. There's not a normal force. Some people are tempted to put a normal force here. Thinking back to here, we had a normal force because this thing right here, this support was pushing up on it. And then the same thing. But here there's nothing pushing up on it in the middle, so there's no normal force. There is a force here at the end though. There's a tension, capital T. And then over here we have these forces that act horizontally and vertically. And so I think it's safe to say that there's going to be a force here, which I'm actually going to call it as I normally call these, which is R sub Y. And then this one's going to be R sub X. And if we think back to the last page, the first example, we had this force, this R sub X, acting horizontally, and it was to the right. But if you watch that video, it made sense because there's a component of this force which is horizontal. Part of this force acts upward, and part of this force acts horizontally. There's a T sub Y and a T sub X. And so this T sub X is to the left, so this force has to be to the right because we're talking about equilibrium, and there's no other force in here that could possibly act to the right. So it must be that the wall is acting to the right. Here, however, we have our force T, which is partially to the right and partially up. And so this force right here most definitely is to the left. R sub X is to the left. And that is all of the forces on that one. Here we'll come over to the next one, and we're analyzing this object right here. There we go. And there is, here let me switch to a different color. I think it'll make it a little easier to see, and I'll go ahead and draw this one in. I'll change here we go. So each of the objects has a weight. So there's the weight of the beam. That's going to be true in this one as well. And then we think about the things that it's touching. So we can see here it's touching that rope or cable, which is straight upward. That is, I'm looking at this diagram now, it looks like it's totally, completely upward. And so here we're going to have an R sub Y. And now you're thinking, okay, which way is this R sub X? Is it left or right? Turns out it's neither. Look at the horizontal forces that are at work. There's no horizontal forces in here, and so there's not going to be any force here. Okay, so we can just make a note, R sub X equals 0. There isn't one. Then right here we've got a bucket sitting on the end, so we've got the weight of the bucket. That's near the end. The center of the bucket is not quite at the end, which is why I drew it like this. And then we've got a cable touching it, and that cable appears to be right in the middle. Something like that. I didn't do a real good job with the angle. In a real problem, you'll be given the angle, or you'll be asked to find it. But that won't be, you can actually label the angle. And then here we've got an R sub X, which is going to be horizontal to the right to offset the T sub X, which is to the left. And then we'll have an R sub Y upward. Then we have a couple more examples we can look at here. We've got this object right here. We can draw in the object. And then same thing down here. I'm going to go ahead and draw in the ladder. And then I'll switch colors. Go with There we go. So the object itself always has a force of gravity that acts right at the object's center. Well, the center of mass, but for a simple object, it's right at the center. We've got the weight of the beam. Here we've got the weight of, I think this is supposed to be a sine. So we have a weight of sine. And then we've got a tension acting, let's say it's right about here. And then here we're going to have an r sub x and an r sub y. So if we look at the horizontal forces, we have only t acting in the horizontal direction other than r sub x. T's a little bit to the right, so that means this needs to be to the left. And then this is probably going to be an upward force. The vertical ones, whether they're up or down, can be a little trickier, but I think all of these r sub y's have been upward so far. All right, finally, we've got this ladder, and there's a fireman climbing up it, and the fireman's weight is balanced on those two steps. I mean, he is touching the ladder there, but I think most of his weight's concentrated there. And then the center of the ladder is approximately right there. So we have the, let's see, that looks like the center there. So we have the weight of the ladder, and then a little further down, we have the weight of the firefighter. And then, okay, well, what else is touching the ladder? Well, the floor is touching it. So there's a normal force here from the floor. And the wall is touching it. So there's a normal force from the wall. And then what else? Right now there's only one horizontal force. So there's no way that can be it. There has to be something else, or else this ladder is going to slide out. And what do you think would stop this ladder from sliding? It would be friction. Which type of friction? Well, if the ladder's not moving, it's static friction. Same thing up here. Static friction. So we'll call that static friction from the wall, and call this static friction from the floor. All right, so that gives you several more examples of drawing rigid body, free body diagrams. Once we start doing problems, we'll be labeling angles. Okay, so if we have a certain angle in here, we'll be labeling like what this angle is and what this angle is. And we'll be labeling distances from our axis of rotation. So for example, if we call this our axis of rotation, we'll be labeling like this is 0.2 meters from here to here. And this is 0.6 meters from here to here. And so on. The distances are going to be really important, and we want to put those on our diagram because the more complicated the situation, the easier it is to lose track of what the specific distances are.